So in the last class, we talked about the borehole logging method. If you remember, self-potential. Right? It captures the potential difference from the electrode at the borehole, the bottom well, and the ground electrode. And if there's an ion exchange, then the set potential can capture the potential difference, and they can tell you whether the formation is permeable or impermeable, right? And the second method was electrical resistivity, and it captures also the resistivity of the material itself, and it can tell you whether it contains the hydrocarbon or water or the gas, right? And what else we did? We did the gamma ray and neutron scattering law and density law, right? And three of them also tells you about the porosity. So the ultimate goal of these three methods, the logging method, is to estimate the porosity along the depth precisely. Right? But only just individual, only one method is not enough. You have to combine so you get more richer information to compare each other, right? And along with those five methods, we'll talk about the seismic, the sonic acoustic log, and the dielectric log, and the two more there, NMR. Okay, the sonic and acoustic log is very simple. You just measure the wave velocity between two sensors. You have one source, and maybe you have two receiver or the one receiver, and if you excite and you can punch it here. If you assume that this is the borehole wall, then you can punch it with the excitation, the source, and you pick up the arrival time of the vibration, because the wave will go through, propagate through the wall of the formation, and you will pick up the first signal. And if you have a second sensor, the receiver, then you pick up the one after that, right? And correlating by picking up the arrival time, you can find out the velocity. So here, it just gives you the idea about how this acoustic log can be used to estimate the porosity. But basically, you're measuring the arrival time between the sensors, and you can convert it because you know the distance between the sensor, and you can convert it to the velocity. And what it does is that it assumes the linear relation between the rock mineral and the pore fluid. So pore fluid is, let's assume that this is water. If it's water, what's the pH velocity? pH velocity of water, 1400? 1400 to 1500, right? 1400 to 1500 meter per second. And the rock mineral, let's say that we have like carbonate or quartz, how much will be the pH? More than 3,000, more than 4,000 meter per second, right? So it's going to be more than 4,000, meter per second. So then, this is the porosity, and 0, this is 100%. If it's 100%, then the rock is just the water, right? So you have the smallest pH velocity. That's gonna be the pH velocity of water, right? And when it's 0% porosity, it will be just the rock mineral. So that will be pH velocity of the mineral. So you just assume the linear line from this to this, and this gives you the porosity, right? So this is very simple assumption. So it ignores a lot of the variation of the rock mineral and the mixture theory and the association between the rock mineral and the water, right? So this doesn't give you a very accurate result, but it just gives you some kind of a rough ballpark number about the porosity. Question? Okay. And okay, but people don't use the acoustic log these days to directly correlate with velocity. They just look at the wave velocity and the change in wave velocity along with that, and they can tell you about what's the fluid composition. Right? For example, if you're if you're hitting hydrate, then because hydrate has a high velocity than the water, you have a very big jump in the wave velocity. Right? If you're hitting the gassy formation, the gas has very low velocity, so it will be very low. You have a drop in the pure velocity or something like that. So this sonic log can be used in the open and uncased bore and least accurate among three porosity logs. Here the three means that neutron and the density and the sonic, these three. Okay? This is useful to geophysicists because it can be used to determine the velocities of formation and relate the timing of the seismic reflectors to actual rock around the borehole. I think we're gonna talk about this one later in the next class. And this table shows the velocity and the density and impedance of various material. So fluid, if it's air, pure velocity is just a sound wave, right? So 340 meter per second. And the pure water, it's about 1480. And seawater, 1500. And oil, glycerin, similar range. And salt, quartz, calcite, you can see that it's more than 4000 meters per second. And limestone, sandstone, and granite, these are the rocks with the pores. So you just get the idea about the range of pure velocity. And when we look at the soil, which is uncemented, not cemented material, it's about 230. And sand is, if it's dry sand, 120 to 170. So this could be you can see there's very low velocity. Ice, 3000 meters per second. Aluminum, steel, and there are more. So, the sonic log or the acoustic log can tell you about the formation velocity. And the next one is the nuclear magnetic resonance imaging. So the NMR, so we use it for medical purposes these days a lot, right? And it's the same concept. And it's the effective way of measuring velocity and permeability. It can differentiate the movable from immovable water. So what it does is that it captures the hydrogen nuclide. So it's just a proton and movement of the proton, the rotational movement of the proton to be specific. So you apply the magnetic field to the material, and if you alternate the magnetic field, let's say that, then the atom inside, hydrogen atom, will respond to this alternating magnetic field, right? So if it's plus and minus here, then I will be directed here if I'm the hydrogen atom. And if it alternated, then I'll direct it here, right? So I'll rotate according to the external magnetic field with respect to the given frequency. Right? So it measures the energy. So magnetic field is external. When the external magnetic field is applied, V naught, the energy absorbed from the magnetic field V1 is proportional to the density of the hydrogen atom. So if you have more hydrogen atom, more energy will be absorbed. So you measure the response of that, and also you can look at the polarization time and the relaxation time. So let's say that I'm the hydrogen atom, and I was randomly moving around in the media, right? And I can randomly vibrate. And when there's an external atom of a magnetic field, I have to be aligned, right? I'm forced to be aligned. And then if this field is gone, then I'm now free. So there will be some time to return to the original random movement. Right? And this is related to the frequency of your magnetic field and also the mass of the mass of the molecule itself. So if you have a movable hydrogen like water, if the hydrogen is in the movable water, maybe it will freely move more. And if it's a bonded water in the clay, then the response will be smaller, or the frequency response will be also different. So from that, you can identify whether this hydrogen is from hydrocarbon, or whether it's from the water, or whether it's from like free water and the immobile water. So this NMR can tell you a lot of information because you can switch the frequency from the low frequency and the high frequency. So resonance of the hydrogen atoms in fluid. But why not the solid? So actually, this is very interesting. It doesn't capture the movement of the hydrogen in solid. Like if you have ice, the response will be very small comparing to the water if you have next to it. So it will give you the, because the response of the free hydrogen is much more obvious than the other one because it's too small. So you don't see it very much and you don't see any difference for the ice. If it makes sense. So when B1 field is switched off, so when the external field is switched off, T1 over T2, the ratio between T1 and T2 is proportional to the pole size. So T1 is, what is it? It's a polarization time, right? Polarization time taken, that's the time taken for the hydrogen nuclide to orient themselves to the magnetic field. And the T2 is the time taken for this to return to their original random orientation. So T1 is the polarization time, T2 is the relaxation time, and this T1, T2 is proportional to the pole size, the ratio of them. So slow polarization and relaxation time indicate the small pores, which will retain the fluid, and fast polarization, relaxation times indicate the large pores, which will yield the fluid. So NMR also can tell you about the pore size distribution. If the rock is all filled with fluid or water, for example. So this can tell you about the permeability of the rock. So actually there are a lot of papers using this method to estimate the pore size distribution and the permeability of the rock. So far, any question? But this NMR is it could be difficult to use if you have a metallic component. Like imagine that, have you been to NMR scanning? So similar to the CT scan, you have to be naked and then you wear just the cotton, right? Cotton gown without any metal. So if you have a metal, in your body seamed in, then they should be notified. Otherwise, it can give you some spark and fun, like the one that you put the metal in the microwave oven. 전자레인지에 넣으면 팡팡 튀죠. 그거랑 비슷하게 NMR 갈 때 중간에 막 우리 철심 받고 이러면 이거를 할 수가 없습니다. So if you have a metallic component in the formation, then the response will be totally different. So you cannot identify or you cannot estimate it with the just ordinary correlation equations. Okay, so dielectric logging. This is the also similar to the magnetic resonance, but the only difference is that you apply the electric field instead of the magnetic field. Before, the magnetic resonance, you use the magnetic force, right? But here, you're applying the electric field, alternating the AC field, and looking at how they polarize according to the electrical field. So the water has the highest dielectric constant. So it's about 70 to 80. And the oil and air, gas are very small at 2.2 and 1.0. And the rock mineral is also small, so 4 to 10. So it can capture the amount of the water in the formation. So higher dielectric constant means that water molecule can be polarized easily. So it tells you about the polarizability. Dielectric constant. So if you have a water molecule like this, and you have a minus and plus, this will, this is the oxygen, so it will rotate this direction so that it will align like this, right? O and H. And this polarization can be, the degree of the polarization can be measured using this dielectric constant. And that's the parameter issue, the physical meaning of it. And this figure is just an example showing that the conventional log comparing to the NMR log. Okay. We'll go a little bit fast. Logging or measurement while drilling. We've been talking about this a lot, right? The MWD or the LWD. You can read this through. And the deep meter log and borehole imaging. So deep meter log is so you have a small electrode at one plane, and you measure the electrical resistivity as you go down, as you go deeper. And difference in the electrical resistivity can tell you about the bedding plan. So whether it's the sedimentary bedding plan. So for example, so direction of the deep bed. So then if this is the bedding plane, and the angle of this is called the dip, and this deep meter log can measure this beta angle. Okay, we can move on. Acoustic borehole imaging tool have been developed, and this is just measuring. So using the sonar and the acoustic, the ultrasound, it can differentiate the bedding formation, and it gives you a kind of a image around the wellbore. It looks like this, and this is the summary of the logging method. You have an electric log, right? Spontaneous SP response and electrical resistivity, and this can tell you of the lithology and hydrocarbon presence and the pressure prediction, and the radioactive logs, so gamma ray and neutron, and the density. This can tell you about the hydrocarbon presence and the porosity. And sonic, because these sonic logs are all affected by the O component, the 4 components, so it will have some information about these, and deep meter. So just a summary showing that the which can tell you which. And examples of the suits of the log with the responses of to borehole. So here, like from the left side, you have a SP, right? And resistivity and conductivity and proximity log. Caliper, this tells you about the borehole size, gamma ray, and nutrient density log, right? And here, sonic, so this is wave velocity. I think you can read this through. So if you look at the textbook, it's gonna be more higher resolution figure. This is a kind of low resolution. So this is a typical logging sheet for the drill hole. And the second homework. So I'll give you the reading of the papers, these arch papers. So you can read it through and then do the homework too. Okay. And we'll talk about the geophysical methods for the petroleum exploration in the larger area. So far, we've seen the logging methods that's only confined to the borehole, around the borehole, right? And we'll talk about the geophysical methods that can be applied to the surface and the 3D structure. Okay. So here, mainly we'll talk about the magnetic and the gravity and the seismic method. So the main geophysical methods are the magnetic and gravity and seismic. And first two of these methods are used only in the pre-drilling exploration phase. So because this magnetic gravity is in the basin scale, so it's like a, I can show you the picture later, but it's like a Ulm basin scale. So, and where is the anomaly, where is the magma intrusion, something like that. So this tells you about very large scale geologic structure or geologic anomaly. And seismic can be very accurate, so it can give you very high resolution information. So the seismic surveying is used in both exploration and the development phase. It's by far the most important among three methods. So let's talk about the magnetic first. So magnetic survey basically measures the difference in magnetic field as you go explore the area. So if you have a magnet, more magnet embedded in the subsurface, you have a strong magnetic field, right? And if you're in the salt dome, which doesn't have a magnet, then you have a weak magnetic field, right? So from that, you can differentiate the anomaly. And here, this tells you the basic information. Earth generates a magnetic field like a dipole magnet. And, okay. Force between two magnetic poles may be expressed as follow, like similar to the Newton's law, A times M1 times M2 over R squared. And so R is the distance between the pole. So, and magnetic field strength is measured either in gammas or in Oersted. Okay. So 1 Oersted is the field that exerts the force of 1 dyne on a unit magnetic pole, and 1 gamma is the 10 to the negative 5 Oersted, and it gives you the numbers here. At the pole, like North Pole and the South Pole, you have a 0.6 Oersted, and the equator, you have 0.35 Oersted. So, at the pole, you have a stronger magnetic field. And the common the horseshoe magnet that we play with, is about 350. So you can imagine that these are very weak and they can be very sensitive to the noise when you measure it. Okay. I think this is just the, if you took the basic, I think, general physics course, you find out that this is J is the intensity of the magnetization, and K is the magnetic susceptibility, and H is the external magnetic field that you applied. So K is the material property here, right? So if you apply like 1 to the iron, then this will be magnetized less than 1, but it will be very strong magnet, right? And if you apply the magnetic field to the wood, and wood doesn't have the ferromagnetism, right? So it would not be magnetized. So K will be smaller. So K will tell you the magnetic susceptibility, and higher K means they can be magnetized more easily. And the magnetic susceptibility of the rock are very wide. The range of those values are very wide. And sedimentary rock is 10 to the negative 4. And iron-rich igneous rock is 10 to the negative 3 to 10 to the negative 2. So if you have the magma intrusion, which is basically the igneous rock, then you have a stronger magnetic field and a magnetic susceptibility. Let me go more. Okay. And this magnetic survey can be carried out on ground, board ship, on the air, using airplane, and from satellite too. It's called the aeromagnetic survey. Okay. Magnetic survey is used in early stages of petroleum exploration, showing the overall geological grains of an area with the orientation of basement, highs and lows generally apparent. And magnetic anomaly maps indicate the presence of the igneous plugs, intrusive, and lava flows, area normally to be avoided in the search for the hydrocarbons. And seismically delineated rifts often been drilled and discovered to be igneous intrusion or volcanic plugs. Okay. So this is the example of the magnetic survey intensity map. It's in Ireland. Okay. And you can see that the minus 500 to plus 700. Okay. And so have a strong magnetic fields may means that you have low basement, so that the igneous rock basement is shallower than the other one. And this is the interpretation one, so it's a similar map. And gravity survey, so I'll tell you the later, we can compare the gravity survey and the magnetic survey together. And gravitational, so gravity survey also measures the gravity force, and gravity force is also very sensitive to the location. And for example, if you are in the mountains area, because we always standardize and compensate for the sea level, if you're in the mountains area because you have a lot of mass from like back to mountain to the sea level, and you have a more magnetic gravitational force. And if you have a light material beneath you, then gravity force will be smaller. And the Earth is elliptic, right? This is the Earth. Like here, you see the polar radius is 21 kilometers less than the equator radius. So here you have I square, right? R, and F is G, M1, M2, R square. So here the gravitational force at the equator is less than the gravitational force at the polar area, because the radius is larger in the equator area. Right? So gravity increases with the latitude and decreases with elevation. Oh, I think I said wrong, right? So if you're in the mountains area, the distance will increase so that you have the less gravity, actually. So correction must be made to compensate the force due to the mass of rock between the survey station and the reference datum, which is the sea level. And these are the anomaly, and there are some equations that can be used to correction. And you can also do free air. Okay. And difference between large density and the low density materials can be captured using this gravity survey. And low density sediment appears as a negative anomaly, and the ridges of dense basement rock show up as a positive anomaly. And so if you have a salt dome, because the salt dome is markedly less dense than most sediment, so you have a low density. And if you have the reef, and this will show up as a gravity anomaly because of the density contrast between the limestone and its adjacent sediment. And reefs are made of limestone, like carbonate, and carbonate is denser than the most sediment. Okay, we'll have to go a little fast. So when we compare the magnetic survey and the gravity survey, let me just, so main use in defining the limits and scale of the sedimentary basin. Okay, here is the example. So if you have a basement, so basement is made of the igneous rock. So it's denser than the other one, and also it's rich in iron. So it has many iron, and it's denser. So you have anomaly, gravity anomaly like this, and this is the magnetic survey region, also the anomaly, the negative anomaly in the sedimentary region. And this shows the same thing. And if you have a reef, which is carbonate, right? Then magnetic survey doesn't show any difference, but because it's heavier than the other sediment, so you have a positive anomaly in the gravity survey. In the salt dome, this is made of sodium chloride, right? So then it's lighter than the other one, so you have a negative anomaly in the gravity survey, and also it's a lack of iron, so it's a small negative anomaly in the magnetic survey. And when you have a intrusion, like this is the magma intrusion, then this is very rich in iron, so you have a positive anomaly like this. So far question, 질문 있니? 궁금한 거? Okay. I have 15 minutes. Good. Okay. So we'll talk about the seismic wave. So seismic wave, the elastic wave, or we call it mechanical wave. And this elastic wave that transfer and that propagates through the Earth's material, we call it seismic wave. And seismic wave is dependent on the mechanical property of the material. So how elastic it is. And this elasticity is expressed in terms of the stiffness. And stiffness, there are numerous types of stiffness, right? These are 4 representative stiffness. The first one is the Young's modulus. And what is Young's modulus? Young's modulus is the deformation for given loading, and you didn't apply any confinement here. So in the Young's modulus, you can see that there's expansion, lateral expansion. So the lateral expansion is allowed freely. And then you can measure the Young's modulus. And the simple shear is a pure shear. You can measure the shear modulus. That's the shear deformation like this. And if you apply the isotropic compression, so you apply and increase the stress all around direction at the same time, then what do you measure? Bulk modulus, right? It's called the bulk modulus. And the last one is the constraint modulus. In this case, you don't allow the lateral deformation. So these 4 elastic constants, E, G, B, and M, sometimes they call N or D, can be correlated each other with the Poisson's ratio, right? So if you learn the materials of mechanics, so then this is, or large M can be used as a constraint modulus. So then this is the correlation between this Young's modulus, Poisson's ratio, bulk modulus, and constraint modulus, and shear modulus. And why we are learning this? Because each modulus can be correlated to the wave motion. For example, P wave motion is related to the constraint modulus, right? And the shear wave motion is related to the shear modulus. And the rot wave, and depending on the boundary condition, the other modulus can be correlated. So for the body wave, I'm not going to detail about the equations here. I'm just want to explain about the P wave and the S wave and the surface mode. So there are two types of the body waves. So first is compression wave and P wave, and the motion is parallel to the direction of the propagation. So here, it's like a sound wave. So I push the air, then you can feel the my push. So then it will be the P wave propagation. So wave goes to this direction, and also the particle move back and forth at the same direction, the same plane. And the shear wave is the different one. So you have a direction of the propagation, and the particle movement will be perpendicular to that, right? So SH, you have two different particle movement. The particle can move horizontally, and particle can move vertically while they propagate laterally, right? So you have a SH wave and SV wave, vertical plane, and you can see the wave goes to X direction, and the particle moves, in this case, how it moves? In the Z direction. So is it SH or SV? SV, right? So then, depending on the frequency, people call it differently. And infrasound, very low frequency, and all state is about 1 to 10 hertz, right? 10 hertz. And geophysical tests in the field, you have very high frequency and also low frequency, and sound wave, ultrasound wave. Sound wave is why sound wave? Because we can hear it. This is the range of the frequency that we can hear. Okay? So 20 hertz to 20 kilohertz. So PA motion and sphere motion. This is the final equation, but the PA velocity is square root of the constraint modulus over the density. So if your material is stiff, then you will have a higher PA velocity. If your material is soft, then the wave velocity will be slower. And shear wave velocity is the same, but it is correlated to the shear modulus, G. Then mechanical impedance. Okay, just ignore all the parts. And here, this is the one that you need to look at more. So Z is the impedance, and that's defined as the wave velocity times the density. Okay? So I'll talk about the impedance more in the next slide. Okay, I think it's the same. And when you have a different boundary, so the body wave is you have a continuum and infinite media. And then you have a confinement by the surrounding material, so you will have a P wave and the S wave. But if you have a different boundary condition, then you get you start to have the different mode. That's called a surface wave. And okay. I think I'll have to. So here. Let's assume that this is the surface, and wave goes to here, P wave. And then this material will extend and shrink, right? And when they want to extend, because of the Poisson's effect, it will become thinner, right? And if they compress, then it will be more fatter, right? But because of the confinement at the top and bottom, it will be hard for the material to expand laterally. Right? This is the case for the infinite medium. It's called the body wave. And so this is the case that you have a confinement. So it doesn't allow the lateral deformation, right? But what about here, at the surface? Because you don't have the confinement here, right? So it will expand to this direction more freely than to this direction, right? So then you start to have a different mode. Before, you have an isotropic confinement to the lateral direction, but now the one side is free. So I can freely extend and expand my material to there when there's compression. So because of that, you have retrogressive, like this kind of a movement. You have a movement this like this, and here, because to balance the force, you have a different mode like this. And this gives you the Rayleigh wave like this. So if you imagine that this is the media, ground surface, and it's filled with the soil, and if I pound it like this, and to the vertical direction, you have a P wave, because it will just go straight, and all the surrounding, the wave is surrounded by the material, right? But what about the wave going to this direction, along the surface? You have a surface mode, it's called surface wave, wave. And also you have a shear wave to the downward. Huh? So I think yep, here. So you have a body wave P and the S wave, primary and the secondary wave within the soil or within the rock, and you have Rayleigh wave at the surface, air soil boundary. And when you look at the energy proportion with the 1 pound, so for example, if I pound it and you have a total energy of this pounding, 67% will be Rayleigh wave, the surface wave will be the most, and the shear wave is 26, and the compression is the 7%. Actually, so yeah, just to give you some idea about the different energy level. So basically, in the petroleum exploration, people use the P wave, not the surface wave, because you want to go deep, right? And the shear wave is too difficult to capture. So normally you look at the P wave signal, and if there's a interface, you have a reflection and a refraction. Right? Reflection is the bounding, and it will come back. And refraction is that you have a penetration, but at a different angle because of the difference in the impedance. 굴절하고 반사 배웠죠? So, actually, I just wanna show you the reflectivity and the reflection coefficient. So depending on the acoustic impedance of the material, you have a strong reflection and small reflection. For example, you have air and there's a mountain. If you say like, oh, then it will come back, right? The echo back. Because of what? The material is different. Here the air is very soft and the mountain is very hard. So it just combine the sound wave, it will bounce back. So in the ratio between this reflection energy is function of the impedance difference. So if you have a bigger impedance difference, then you have a stronger reflection. If the material is similar, so for example, I'm talking to a rock here, and that rock is connected to that wall, concrete wall, and this concrete and the rock have the same similar PA velocity and density, then this would just it penetrate, go through it, right? Will bounce back. So this is just the and geophysicists in the seismic exploration, they use this kind of a reflection wave, and impedance is the function of density and the velocity. I'll show you the example. So this is the sketch showing how seismic data are acquired. In the case of offshore exploration, you have a boat towing a lot of sensor array. So you have a energy source. It could be dynamite or the air gun, and you have a array of geophone or the hydrophone, and you detonate the explosion here. The wave will generate it, and it will go through, and some will be reflected to here, and some will go deeper, and then will reflect it at the different boundary. Okay? So you capture the reflective wave using this hydrophone. And again, if you capture it from this geophysical survey, and you'll be able to get this kind of signal. So one signal is this one, and the signal is aligned horizontally, so that it is displayed in the plane. Then the reflection, probably this is the seafloor interface between the water and the sediment, and probably there's another, like the boundary. It shows the different geological formations, something like that. And the fault too, you can find out the fault here. So here it shows some fault. So reflection and transmission. So we'll talk about a little bit about the reflection and transmission. Okay, first, you have the water and the water saturated soil. And P wave at water is about, how much is it? 1500 meters per second, right? And the water saturated soil, the P wave velocity is about 1900 meters per second, right? 2000 meters per second. So this is about 1500 meters per second, and 1900 meters per second. Or here, this is better. And what's the density? Density here is about 1000 kilogram per cubic meter. And here, the saturated soil has a density of about, 1.9. Let's say that 2, so 2000 kilogram per cubic meter. So then, mechanical impedance will be more than twice the difference, right? So you have a P wave going from soft material to the stiff material, right? In this case. What about in the gas saturated soil? P wave velocity is about still the same, right? 1500 meters per second, 1000 kilogram per cubic centimeter. And gas saturated soil is less than 1000, less than 9, maybe 500 meters. And the density, how much would that be? About 1500. Right? So the impedance of water will be higher than the gas saturated soil. So in this case, the P wave is started propagating from stiff material and leaving the soft material. Right? So it's gonna be the different situation. And what happens if we have that? Okay. So you have a coupling point. This is the interface. Here you have a stick material with a bigger rod, and you have a smaller impedance, the soft material, right, at the junction. So then what happens if you're propagating the wave? So you have an incoming wave from right side, right? Because the soft material, and you have a hard material at the left side, and the reflection is inverted, right? And you have still the same shape going through to the hard material. So this is this magnitude and the inversion and the positive peak and the negative peak is related to the reflection coefficient. Can you see it? It's a small, it gets very small, but you have an inverted magnitude. So this is because of the impedance mismatch. And one more. Fixed end and the free end. So fixed end is like the rope is fixed to the wall here, and you can think that it propagates from the soft to the hard material. Right? If you have a free end, this is just the air. So from hard material to the soft material. Right? So what happens in the fixed end? The wave gets inverted. Right? But here the free end, it just go to with the same polarity. Right? So again, you can look at right. Okay. Then I think we're almost done. I'm gonna do it again. Okay, before I think we need to stop here, and one last one, then we're done. Okay, this is the quiz. Can you see well? So now you have an incident pulse with this shape going to the free end. Right? It's not fixed. Free end. What will be the reflective wave shape? A, B, C, D. If the free end polarity is the same, right? It's kept same. So A, A. Any other opinion? So let's check A. And the second one. So now you have a fixed end. So it will be inverted, right? A, B, C, D, what would be your choice? B, A, A, B, B. And now you have a two different material. So left side is soft, and the blue one is the stiff one. So then it will be like more like your fixed end. So then what will be response? A, B, C, D. So this one, so it's going to be inverted, but the shape will be the same in the media B. So which one? C? You agree? So this is gets inverted, and transmitted one also it kept the same shape. So the last one. So from the dense to the thinner stream. So this is gonna be the will act as a free end. Then will be the same polarity and the same. So which one? A. Okay, if you agree, click the A. Huh? Okay, view the correct answer. Oh, good. One A, B, C, and A. Good, great. So there was so you get the idea about the reflection and the transmission, right? Depending on the mechanical impedance. We'll continue from here next Friday.